So as we start 5.8, we need to introduce three new integrals. In the last section, we looked at the derivative of inverse trig functions. And one thing that we notice is that the derivative of inverse sine and inverse cosine were essentially the same thing. The derivative of inverse sine was u prime over the square root of 1 minus u squared, where the derivative of inverse cosine was negative u prime over the square root of 1 minus u squared. Now, yes, those are different, but the only thing different is their sign, is the positive or negative, which means when we go to integrate, if we were to integrate this, so if we end up with du over 1 minus u squared, that's going to integrate into inverse sine of u plus c. If we were to have a negative here, instead of having a whole nother formula, say, well, if we've got a negative there, it integrates into inverse cosine instead, we could just pull that negative out front. So if that negative is just a coefficient that we can put out front, there's no need to have one formula and say that integrates into inverse sine, one that goes into inverse cosine. We can basically combine those. The same thing holds true for tangent, cotangent, secant, cosecant. So our formulas are that the integral of du over, instead of calling it just 1 minus u squared, we're going to say a squared minus u squared, because we could have a number other than 1 there. That's going to turn out to be arc sine, or inverse sine, u over a plus c. If we have du over a squared plus u squared, remember the ones that when we took the derivative didn't have a square root on bottom, that was the tangent and cotangent. So that integrates into arctangent u over a, but we also have a coefficient with that. We have a 1 over a in front of that. And then we have one more. We have du over u square roots of u squared minus a squared. That integrates into 1 over a arc secant absolute value of u over a plus c. So those are the three integration formulas that we're going to introduce. And remember, an antiderivative is just going backwards from a derivative. So from the derivatives we had in 5.7, the derivative of these things, we got those. So we're just going backwards. So let's do this problem, and I'm just going to bring this one over to another page. Let's integrate. What did we have? We had 1 over x square roots of x to the 4th minus 16 dx. So we have three new integration formulas. That doesn't necessarily mean that any of these problems are going to use those formulas, but so we have to keep in mind other techniques. But since these are in this new section, there's a good likelihood that one of these three new formulas is going to be what we're looking for. Now notice we have a variable squared here minus a constant. So if we look at these, this one has a constant minus a variable. This one doesn't have a square root. This one has a variable minus a constant. So most likely, we're going to be trying to get this into the form du over u square roots of u squared minus a squared. This bottom one. So if that's going to be what we need, then u squared is going to be x to the 4th. If we take the square root of both sides, that would mean u is x squared. A squared is going to be this number, 16, which means that a would be 4. And if u is x squared, then that would make du 2x dx. So we have a couple of things, good things, a couple of things that don't match. This is u squared, this is a squared, but notice this is not u. U is supposed to be x squared, we just have an x there. Well, we could fix that by multiplying that by x, as long as we also multiply the top by x. We can't put that variable outside of the integral, so if we pick up a letter here, we have to pick up the same letter on top. So that makes this part our u. Our du, earlier we didn't have an x to go with that dx, now we do. The du needs a 2 to go with it. So if we can pick up a 2 there, then all of that would be du. And if we multiply the top by 2, we have to put a 2 on bottom. Since that's a number, we can put that out front. So you don't have to rewrite this, but just to show you where everything is, I'm just going to rewrite it like this. So this is du on top. That's u square root of u squared minus a squared on bottom that we're trying to integrate. So that integrates into front. And to integrate that, we need 1 over a, so 1 over 4, arcsecant, absolute value of u, over a, plus c. Since x squared is always positive, we do not have to leave that inside absolute value, so we can call that 1/8 arcsecant x squared over 4 plus c. Or if you'd rather use inverse secant like that notation is okay as well. So that's how we'll go about doing that first one. And one of the biggest keys or clues on these is, first of all, do we have a square root on bottom? If we do, then can we write it as a constant squared minus a variable squared? Or is the variable squared the positive one, and then the constant the negative one? That's how we differentiate between those two. This one doesn't have a square root on bottom, so it kind of stands out from the other two. So this one, notice this one doesn't have a square root on bottom. So let's see if we can make this du over a squared plus u squared. So if we can, this would be a squared, and this would be u squared. So if a squared is 9, a would be 3. If u squared is e to the 4x, then u would be e to the 2x. Think about if we take the square root of both sides. Taking the square root of something is like raising it to the 1/2 power. If we have a power to a power, those get multiplied. So 4x times 1/2 is 2x. So that would be u. Du would be the derivative of that. So the derivative of e to the 2x, remember that derivative of e to the x is, or e to the u is e to the u times u prime. The derivative of the exponent is 2, and that's dx. We have e to the 2x, we have dx, we need to multiply by it. So that gives us 1/2 the integral of du over a squared plus u squared. So if we look back at our formula to integrate that, we have 1 over a times arctangent or inverse tangent u over a, and then plus c. So 1/6 arctangent e to the 2x over 3, and then plus c. So it's just recognizing the form we have, picking what we think is a squared, what we think is u squared, and using those to get a, to get u, to get du, and then seeing if we can turn what we have in to our formula. And in this case, we were able to. So let's look at one that has some trig in it. So this one has a square root on bottom. It has a constant squared minus something with a variable squared. So let's see if we can make it look like this one. So if it is, then a squared is 25, and a would be 5. If u squared is sine squared, then u would be sine, and that would make du the derivative of sine, which is cosine x dx. So what do we have? We have cosine x dx. That's our du. That's our a squared. That's our u squared. So that's our arc sine. So that integrates right nicely into arc sine of u over a plus c. Now, if we didn't have this 5 here, then inverse sine of sine would undo each other because that's the composition of inverses. But since we have that 5 there, we can't just simply pull that 5 out, or we can't divide that letter by 5. That doesn't quite work. All right. So here we have a definite integral. And notice there's no square root on bottom. So if it's going to be one of our new formulas, then it would have to be du over a squared plus u squared. Or it's perfectly fine to put the u squared and then the a squared. It doesn't matter since they're added. But this one is going to be one of our first ones where we've had to complete the square. That's a constant, but that's not something squared. We can't just simply say, well, u squared is x squared minus 2x, and then take the square root of both sides. That's not a perfect square. So what we want to do is we want to use the method of completing the square so that we can write this with possibly another number as a perfect square trinomial, and then we would have another number to go with this, and that would be our a squared. So let's see how that's going to work. So I'm going to make some room, and let's put our x squared minus 2x, and I'm going to say let's put plus a number there, and then we're going to have plus 2. And in the past when we've completed the square, they typically were not in a fraction. So they were usually in an equation, and if we add a number to one side, we just add that same number to the other side to keep it balanced. In some of the previous examples, if we were missing a coefficient or a factor, we could just multiply the top and the bottom by the same thing. But if we have a fraction, it doesn't work to simply add the same number to the top and the bottom. We can't do that. 1/3 and 2/4 are not the same thing. So what we can do is if we add a number, we can subtract that same number. Think about it. If I add 3 and subtract 3, I have a net change of 0. So in this one, remember how we find the number that goes there? We take half of the coefficient of x. So we take half of that number, and that answer we square. So half of -2 is -1. -1 squared is 1. So if we add 1 here, that's a perfect square. If we add 1 there and subtract 1 there, we still have the same net amount that we had at the beginning. Notice we have an x squared, a minus 2x, 1 plus 2 is 3, minus 1 is back to 2, which is how much we needed. This trinomial factors to x minus 1 times x minus 1. We can express this as the integral of dx over x minus 1 squared plus 1. So we have a variable part that can be written as a square, and we have a constant part that can be written as a square. So if u squared is x minus 1 squared, then that would make u x minus 1. Du is the derivative of that times dx. If a squared is 1, then a would be 1. We have the integral of dx is du. On bottom, we have u squared plus a squared. So we could integrate that and change it back into x's and plug in 0 and 2, or we can go ahead and change our limits. We know the relationship between u and x, so this is an x value, that's an x value. So if we want to change it to u values, when, let's see, if x is 0, then u is 0 minus 1 or negative 1. If x is 2, so when x is 2, u is 2 minus 1 or 1. So that changes those limits. Those values are now in terms of u and not in terms of x. So that antiderivative is 1 over a, which our a is 1, arctangent u. Oh, we're not changing back to x's. U over a, and we're evaluating that from negative 1 to 1. So 1 over a, arctangent u over a, and since we changed these to u, negative 1 to 1. So we get arctangent, put in a 1, minus arctangent, put in a negative 1, and we check those. Imagine we want to do these in radians, not in degrees. So some of your calculators will do this and give you an exact value. If I just take my calculator out here and I put in a 1 and I put it in radians and I say, what is arctangent? It's going to give me a decimal. Remember how we do this calculation. This is a ratio and our answer is an angle. So we're looking for what angle has a ratio of 1 for tangent. In other words, at what angle is y over x equal to 1? Tangent on the unit circle is y over x. Well, in order for y over x to equal 1, y and x have to be the same. Well, the only place that happens in the first quadrant is at pi over 4. At pi over 4, that's root 2 over 2, root 2 over 2. Those make 1. So this is pi over 4. Tangent is negative in the fourth quadrant. And if we pick this value, then the y value over the x value is negative, and that's root 2 over 2, negative root 2 over 2, root 2 over 2, negative root 2 over 2. Actually, it's the other way around, because the y is the negative one, the x is the positive one. But regardless, that fraction equals negative 1. That is in the direction of negative pi over 4. So a little review of trig there. But that comes from your unit circle. I would be fine if you typed it in your calculator and gave me a decimal, or if your calculator will give you exact values, that's fine. Minus a negative makes that a positive. We have a common denominator. So we get 2 pi over 4, or that reduces to pi over 2. So plugging the numbers in was a little bit tricky there to find out our final answer. But one of the main emphasis I wanted to make there is completing the square so that we could get our antiderivative. If you don't like leaving it in terms of u, if you like changing it back to x's, we would have ended up with the same thing, and you could have done that. We could have called that the integral. When we did du over u, the answer to that would have been 1 over a arc tangent u, which is x minus 1, over a, and in terms of x, we were going from 0 to 2. Well, if we put a 2 in, 2 minus 1 is 1, so we'd be taking arc tangent of 1. If we put a 0 in, 0 minus 1 is negative 1, so we would be taking arc tangent of negative 1. Same thing we ended up doing down there. So you can either change your limits to u's, or you can get your antiderivative, change it back to x's, and then plug in your x values. So let's do one more. Notice on this one we have a square root on bottom, and our square part is negative. So the formula that we had that had a square root on bottom and the variable part that was squared as negative had an a squared minus u squared on bottom. So which one had the a squared minus u squared? That's the one that gave us arc sine. So we want to see, can we rewrite this as a squared minus u squared? So let's go to another sheet and see how we can rewrite this and try to make it a squared minus u squared. So if we're going to have a minus u squared, we're going to have a negative in front, but the square is going to be on the u before the negative is applied. In other words, we're going to need to factor this negative out. Let's change the order of this before we do so. Let's call this minus x squared plus 4x. And we want the x squared part to be positive, so factor out a negative and call that x squared minus 4x. Now we want to complete the square in this parenthesis so that we have something that's being squared there with a negative out front. Something that's being squared with a negative out front. So if we take half of this number, we get negative 2. Negative 2 squared is 4. So 4 is the number we need to add there. So that would make it seem like we need to put a negative 4 there. But do we? If that's a negative, keep in mind that negative applies to that whole parenthesis. So if we were to distribute it, we would have a minus x squared, check. We would have a plus 4x, check. When the parentheses are gone, that's really a minus 4. Well, if we're wanting to put the opposite of a negative 4, that should really be a plus 4 there. So if we were to distribute that negative, combine like terms, this positive 4 and that negative 4 would cancel. But we need that 4 there so that we can so that our polynomial is a perfect square. So that polynomial factors to x minus 2 times x minus 2, or x minus 2 squared. So that's a squared, and that's u squared. So we're going to rewrite this under the radical as 4 minus x minus 2 squared. And then we have 2x minus 3 dx integrating from 1 to 3. So we have part of our problem fixed. We have that we have an a squared and a u squared. So if that's the case, u would be x minus 2 and du would be 1 dx. A squared is 4, so a would be 2. But hold up. So if u is x minus 2, we need just dx or a constant on top. We actually have a constant combined with a variable term. So that presents a little bit of a problem. What is one thing we've done in the past in algebra? If we only need one of these and not both, we could actually break this into two separate fractions. We could 2x over the square root and then minus 3 over the square root. And that's dx. So 4 minus x minus 2 squared. When we look at this one is really close to what we need. If this is a squared and that's u squared, then we need 1 dx on top. We just have an extra number on top. We can't just simply pull this 3 out front, because if I put a 3 there, that 3 applies to both terms. Not just this one, but both. The easiest thing to do is to break this into two separate integrals. One integral where we do 2x over the square root dx, and then one integral where we do 3 over the square root dx. So for this one, we just need a 1 on top. So we come in, we take that 3 away, we put it out front, and that leaves us an understood, or I'll say not an understood, but leaves us a 1 there. So for this one, that's a 3 times the integral du over the square root of a squared minus u squared. Now, you might be wondering, why have I not put anything underneath that square root? That square root is the same as that one, and that's exactly right. But the reason I haven't put anything under there yet is because I want you to look at that numerator. In our integration formulas, if we had an a squared minus u squared, and then we had a du on top, we didn't have a variable up there. We didn't have a u also. So what are we going to do if, went back one too many. If we have a variable up there that we don't need? We can't just pull that x out front. We can only pull coefficients out front that are numbers, not letters. Well, let's look back at our original problem here. If we would have not known that formula, if we go back all the way to when we first start integrating, one thing we do is we make a substitution. So sometimes when we do a substitution, we take what's underneath our radical, or what's the most inside function, we let that be u, and then du is just the derivative of that. So the derivative of that would be 4 minus 2x dx. Hey, I see a 2x. So that's essentially what we're going to do here. So let's take this back to where that's supposed to be x squared. So long story short, if we have a 2x here, we don't need the denominator to be in a squared minus u squared form. So what are we going to do with that? So I'll try to do this without getting terribly messy. But if u is 4x minus x squared, and du needs to be 4 minus 2x dx positive 2x. So let's this a closer fit. Let's factor out a negative here. If we factor a negative out, we would have 2x minus 4 dx. So how do we make this work? If all of that's u, and we want to have a du on top here. So if we could subtract 4 as long as we also add 4, and we would also need to multiply that by a negative. If I multiply by a number here, I have to divide by, so I'm basically multiplying by negative 1, divide by negative 1. So I think the best way to do this, I'm going to erase a little bit and let's go back and re-explain. So we started out with a 2x up here. So we need a 4 taken away from that. If we take away 4, we also need to add 4. And the 2x and the minus 4, we need to multiply that by negative. We can't just simply multiply part of the numerator by negative. We have to multiply the whole numerator by negative. By negative. So let's move this. So we have a negative 1 out front. We don't really need that part. We have to have it to keep it equivalent, but as far as our integral, we don't need that part. So let's take that 4 out. If we take that 4 out of the, that's really been multiplied by a negative, so we have a negative 4 up there over the denominator. And so bring this down again. Keep in mind that even though these denominators look differently, they're still the same. And we had a 3 up here that we weren't really needing up here. And we pulled it out. This minus 4 we don't need in this integral, so we can just take it and put it over here with the other integral as part of its numerator. So just to make life simpler, let's do that. So we're adding negative 3 over that square root because that's what we had, a negative 3. When we made this numerator fit our du that we needed, we can take this negative 4, take it out of there, and we already had a negative 3 on top here. We can put that negative 4 with it. Even though the denominator looks differently, it's equivalent. So, man, that's really messy. Let's see if we're equivalent to what we started with. How are we going to see if what we have is equivalent to what we started with? Well, we just need to recombine our fractions. We have the same denominators, even though they look differently. We have a minus 2x. We have a plus 4. And this negative says we take the opposite of that. Then over there we have a minus 7. So that makes 2x minus 11. So that tells us there's a sign wrong somewhere, because we're only supposed to have minus. So okay, I think I found out where our issue was. So it's all of these negatives. So it's right that if we have a minus 4 here, we're supposed to have a plus 4 there. And then when we take it out of this parenthesis, that makes it a minus 4 there. What the mistake was is if we move it over here, that still times this other negative. So if we were to break this into two separate fractions, that negative would go to both of them. So this should really be a plus 4 there. So if that's a plus 4, then that's a 1 there. So we have a minus 2x plus 4, that changes those signs. Minus 3 plus 4, that makes this a plus 1. Minus 4 plus 1 is minus 3. That's what we have. Okay. So we finally have our constants and everything like we like it. So we have a negative out front. This is du over the square root of u. Here we have 1 dx, which for that dx is du over square root of a squared minus u squared. So it turns out we didn't have a number over here we were going to have to pull out. So if we go back and look at, for that one, du is dx. So dx is du. That was a squared, that was u squared. So we just need to integrate both of these. And once we integrate both of those, then we can change them back to x. So for this one, that integrates into arc sine u over a. For that one, u is x minus 2, a is 2. This problem here, if we're integrating that one, we have our negative out front. And if we integrate du over the square root of u, that's really just u to the negative 1/2 du. That's u to the 1/2 on bottom. If we move that to the top, that's u to the negative 1/2. So that makes u to the 1 bigger power over 1/2, or times 2. So the negative out front, 2 u to the 1/2, which is the square root of u. And for this one, u was everything underneath. So that's our full antiderivative, and we want to evaluate that from 1 to 3. So for time's sake, we're not going to plug in all of those numbers right now, but you could just plug a 3 in, get that as a decimal, plug a 1 in, get that as a decimal, and then take the difference. So I know this last problem was a little messy, and I'm sorry that I kind of made a mistake in there and got a couple signs wrong. But most of them won't be that complicated, but that did introduce a couple of techniques. Often we haven't dealt with adding and subtracting on top and trying to fit our u's and our du's.